So getting a little deeper into this. So you've probably already noticed this about statistical models in general, the ones that we've gone over so far. There are always assumptions involved with those statistical models, which is a little frustrating. And it is really important to keep in mind these assumptions. So I'm working with someone on a project. They're not a statistician. They work in finance. And in the way he's seen things done, a lot of times is they throw linear regression at everything, whether it's the best model or not. And I have tried to explain to him why that's not a good thing to do. So assumptions in general, they make rules that our data has to meet certain criteria. And if it does not meet that criteria, you should not use the test to look at that relationship. So I'm going to go over assumptions of correlation and assumptions of linear regression. And if you find that these assumptions aren't met, that means that your results are pretty much meaningless unless they're very, very strong in one direction. And even then, I would not use them. So that is the downside of linear and logistic regression. And correlation as well. They have a lot of assumptions involved in them. So what if they don't meet these assumptions? That means that we then have to use a different statistical test or transform our data. So what transforming our data would mean, maybe finding the square of all of our points on our line. It might mean finding the square root of them, and it sometimes makes something that looks like this. If you ever see this in your data, any pattern whatsoever. So going back to this, we see that it very clearly follows a linear trend. So we could draw a straight line through this, and then the dots are randomly distributed around what we would put that line through. So, excuse me, this is what you want to see. So a very linear trend, it follows a line and random distribution throughout. We're going to go more into what I think we need to mute microphones. I'm going to having a lot of feedback on my end. So if you see a pattern that looks like this, say you see an S pattern, say you see something that looks like a curve going this direction. If it's a strong curve, and we're going to look at how to test this mathematically a little bit later, but in general, if you see a strong pattern, no matter what the pattern is, that's a problem. So you would, and I can go over this more next week. I wanted to go over the basics, but you may have to then transform your data by finding the square root, the square, so on and so forth. And if that doesn't work, you might have to use a different statistical model altogether, in general. I do see that more often. In practice, transformation didn't usually get rid of the problem with real data. So the great thing about machine learning and why it's so widely used is because it doesn't assume linearity for the most part, and it doesn't have a lot of assumptions involved. So that is why it's used in data science more often, because data usually isn't perfect. So more on the assumptions. So both variables must be continuous. So by this, let's go in and look at our linear model data. You see here that these aren't integers. If they're integers, that might indicate that it's maybe a rank or something that is not a direct measurement. So here you're seeing the mortality rate. This is a great indicator that it is continuous. If these variables are not, they don't have just 316, that doesn't necessarily mean that it's not continuous if you have 316, but it might be an indication that you would want to look more into it. One thing that in general, so say we had an example is when I was looking in one of my projects, an agricultural project that I did, we had data that was a rank. So we looked at, and I can give an example, say a disease, a plant disease. We had a rank from 1 to 100 based on how strong the disease was, and I believe that there were definitions for each. So that is something you would not want to use the correlation coefficient for, because that's a ranking from 0 to 100. You're not going to, and a rank is something that you can't use with the Pearson's correlation. So you would want to use something that looks more like this. More on that. So Michael brought this up already. If you have ranks or something very similar, you want to use a rank correlation. And Spearman's row is the name. It was named after him who found it. But rank correlation and Spearman's row mean the same thing. So just a synopsis, like I said, I'm not going to go over this in detail because there's just a lot of material here and it's very similar. It's very similar to the Pearson's correlation with one caveat. So in here, let's go and say for some reason we wanted to use the rank correlation. Rank correlation tends to be better even with continuous data. You would use it if you have a lot of outliers and your outliers were meaningful and you couldn't remove them. So this data, say what it does on the back end and with the math is it ranks these from 1, and we have 3,141. It's going to rank our values from 1 to 3,141 and find something that's very similar to the correlation. And it's going to do that for both of our values we're trying to find the relationship between. Why does this help with outliers? It makes sense because it's going to put it on a standard scale. So even if, say, you have one really far out outlier, it's not going to be very far out in your data when you actually find that rank. It's going to be, they're going to be close together. You do want to use, if you can, the Pearson's correlation is going to give you more information, and it will give you, it's the better test to do if it meets the assumptions. And I think we have a question here. So formula from the book. Yeah, so I will definitely look at this later and try to explain if it's the same or how it's different, and we can clarify that. So the first one is that it's continuous. The pairs of observations must be independent. So what does that mean? Let's go in. So if we were finding, and I'll just do these two because they're side by side. Okay, say we're trying to find the correlation between the mortality. Actually, that is a terrible explanation. So let's do life expectancy and percent high school graduate higher than 2014. So the life expectancy, what it means is independent pairs, is that this 86 number, the life expectancy for each pair, one pair, so this value should be independent from this value. So one should not depend on the other. The reason why I started off with this example, this is a great example of when you shouldn't do this. So this is heart disease mortality rate. And this is life expectancy. There is, to some extent, the life expectancy, some of the people that die and that there are included in these life expectancy numbers, the lower ones, a lot of them, heart disease is very common. So there's going to be a relationship where these are not independent. This is somewhat included in life expectancy. So that is an example of when you would not want to do that. Whereas life expectancy here, there might be an association, and that's what we're testing, but this is not dependent. They are not dependent on one another directly. So that gives you a great example of what it would be independent and what would be dependent. Is there a question?
Yeah, when you say dependent, is that another way to say causation?
No, it's actually different.
Okay.
So, so this is not going to cause your life expectancy to be to increase by default. Say this could be what would be an example? An example of a more rare disease, say pancreatic cancer. So if I use that as an example, pancreatic cancer, I believe, is a lot more rare than heart disease in general.
Yeah.
But so there wouldn't probably be a strong dependence between those two, but you still wouldn't want to do it. So another example, we were, and I can't give exact details, at one of my jobs, we were looking at a waste value, and we were looking at some type of sales metric. But when the first time we went through, we actually found that the waste in the back end, the formula included sales in it. And just because it was and we hadn't actually calculated those numbers ourselves. But when we look back at the formulas, we looked and saw that one value was a component for calculating the other. That's how you could think about it here. So and we actually had to change our methodology to remove that problem. So this is going to be included in the calculation of this. However, heart disease mortality does not cause a life expectancy increase. Why? Because there are a lot more factors involved in life expectancy. So you're going to see that heart disease, Alzheimer's, lung cancer, all of them together cause this. But if we're looking at one value, say one county might have really low heart disease. Say in Denver, there's a lot of exercise, and in general, in the population, we're seeing a lot less heart disease than the place that I'm from, for instance. In Pennsylvania, Franklin County, heart disease is really common because obesity rates are very high. So, but at the same time, in Franklin County in Denver, the life expectancy, theoretically, I have no idea if this is true, could look similar. Why? Because there are so many other factors involved in calculating this. So basically in Denver, hypothetically, they have a disease that is much more common than in Franklin County that causes life expectancy to be low. So they might have the same life expectancy, but the factors contributing to that could be totally different. So hopefully that helps you understand the difference between if something is dependent. So if one value is used to calculate the other value, which is definitely the case here, versus causation, which one always, like, as one goes up, it causes the other to go up. And we're going to talk more about causation in a little bit. But does that make sense? If there's any more questions about that, I can stop.
Yeah, I mean, I think what you're saying is that the life expectancy is calculated directly from a bunch of different statistics that include heart disease.
Yes, heart disease is one of those. Exactly.
Versus life expectancy isn't based on the percentage rate of graduation.
Yes, correct. So these might have a relationship, whereas, and we're going to actually look at the relationship between these two variables. But just because you had a higher education, that does not, like, it's not included in the calculation of life expectancy. They're two totally different concepts, whether related or not.
But they may be correlated.
Absolutely. And that's what we're trying to test. But that's what this assumption, going back to it, they have to be independent of one another. One cannot be used to calculate the other. And the reasoning for this makes sense. So say you have that waste value and you have your sales. If one is included in the other calculation of the other, the correlation is going to be artificially high, because that is actually included in the calculation of the other. And when we're looking at waste and sales, they in reality could not be highly related. But if the same number is used in both of the calculation of both of those, then it's going to make those numbers more similar, whether there's a relationship or not, because the formula includes the same value. So that's why, in a mathematical terms, why this is an assumption. So this one in general, for every statistical model, this is important. Everyone you'll ever see, machine learning, not. no major outliers. So I get the question about when to take out outliers versus not in a lot of cases. So I've gotten that question a lot. So in this case, I'm actually going to show an example, and we're going to go over more about this a little bit later. But I would like to show it because I think it would help with understanding of this.
And when you remove the outlier, you remove the entire vector from the data frame.
Yes, you have to remove it, and I'm gonna go over kind of again when you would want to remove versus not. So, okay, this Cook's distance, and we're gonna go over more of this when we get to linear regression. So this, I'm not going to go into the calculation of it, but it means that if it's higher, it's going to be more extreme of an outlier. So what this is looking at, we actually, in this case, and we're going to go over it later, we fit a linear model, and this is showing the influence of each data point on our model. So we're seeing that everything has a Cook's distance below 0.01. And this one has an influence measure that's 0.04, which is fourfold higher than the rest of these. So if, say, we use this in our correlation, which we're talking about right now, this would bias our results. It would cause there to be a bias in our correlation, and the relationship might be there, but it's going to mislead you in the number, how high that is or low that is. So these outliers are going to basically ruin your model and give you incorrect information. So when to take out or not? So here we have 3,137 counties. We have this as an outlier. It will definitely bias our model. There is only one. So if there are a lot of outliers, there was a rule of thumb in agriculture, and I believe it's in statistics in general. Say you had a lot of outliers. If you're removing more than 5% of your data, if it's you have a problem there. So say you have outliers, 10% are outliers, and our data is very highly dispersed. Please mute our microphones again. So that value, if it comprises 10% of our data, if we take them out, then our model is going to become biased again. So if we are removing too much, then you don't want to remove the outliers. You probably, in that case, would want to use a different statistical test that could handle outliers. However, here we have one county in our data set that is an extreme outlier. We'll be pulling one is a very small percentage of our data. You want to try to conceptualize if removing it will highly bias your results. However, if you have something that is this huge of an outlier and you keep it in, that's not really an option. So you have to weigh the different pros and cons here. So I would recommend saying if you see something that is this high of an outlier, you need to ask, is it a meaningful outlier? Does it give us more information? In this case, probably not. It's not going to add that much information to our model. So that's the first question. Do outliers add information or give you information? The answer is yes. Find a model that can better handle outliers. Are we removing too much of our data? The answer is yes. Then again, you need to find another model. If there are a couple of them and you won't substantially lose information when you take that outlier out, and we should still be able to see the relationship pretty clearly, but what we're trying to measure, then I would recommend removing that outlier and doing the statistical model. What isn't an option for most models is if you have several large outliers and you just run the model anyway. That is not good practice in this case, and you're going to get a result that is not, it's not true to what is actually happening. So that gives you some more information about outliers. And the last one, which I've talked about a little bit already, the data must be linear. going back to here, again, that means that there is you could basically draw a line through it, and it's somewhat randomly distributed around that line. Whereas if we're looking here, we can't draw a straight line between these to measure this relationship. It does not describe the relationship. You would have to do somewhat of a quadratic formula to explain this. In that case, you either need to transform your data, which in my experience often does not work. In this case, it probably would, because it's a very clear formula. It's definitely quadratic. So you could probably handle this, but in real life, actual practice, there are very few times that transforming my data actually worked, but you should try it anyway because it's an easy fix, and then you can use the linear model. If transforming your data does not make your data linear, then you need to find a different model to use. So in general, patterns are bad. If it doesn't follow a straight line with like randomly dispersed points around it, then that means your data isn't linear. There are any questions about that?
So do you have a scatter plot of that data that you were showing on the
Yes.
on the Cook's
Mhm.
distance?
So this one is, I believe it's mortality. Well, I do not use a scatter plot actually. So if I go down here, I can't remember which variable it came from. Okay, I thought I had run that the whole thing.
That's okay. I can ask it in a different way. Yeah. So it seems like that what that Cook's distance is telling us is that the standard deviation of that data point would be much higher, and so that's an input into the denominator, which is going to skew the formula results.
Not exactly. So it's beyond the scope to go over the formula, but it's actually how much, say if you ran the model with it and ran the model without it, how much did our results change? Is a better way of thinking of it. So if I saw this, and we'll get to it later, but these outliers, you would want to check those Cook distance on these outliers, any of these, because all of the dots are outliers. But just because it's an outlier on a box plot does not mean it's actually meaningful in practice. So you would want to run something like the Cook's distance, which on the back end is running the model with it, running the model without it, and how much did our results change. This one, I believe, had a larger outlier. So that's odd. I didn't think that they looked that similar. Okay, this is the one. So percent high school graduation higher than 2014. So this is the percent of people that graduate from high school. There is a county out here that has everyone at 100%. So when I would see that, first thing that I would suspect is that this is wrong. How can a county be? I mean, it would have to be a very rich, affluent county for every single person or very close to it to graduate from high school. So I would assume that this might be an error, to be perfectly frank. And even if it isn't, this point is going to have a high influence on our model, and it absolutely would need to be removed.
Or they only had like 3 people in the graduate class in 2014, yeah?
Yeah, so that's something, and that's a great example of something that would be removed. It's not adding information here. It's so weird that it's not going to help us explain the relationship. So that's another example of when you would absolutely want to remove it. Outliers are sometimes data entry errors or data errors, and just because it is a government data set does not mean it's right. I say that because I have used very highly used data from the government. In this case, it was Medicaid enrollment data. And since this was at a university, I can say this, and there's no proprietary knowledge here. I was using Medicaid enrollment data by state. I got Medicaid enrollment data by county from the actual state, and they were supposed to be reporting that county level data to the state. So it should have theoretically been the same, and it wasn't. And I did a lot of investigation to see, because there's a lot of ways that you can look into that and try to figure out which one's right, because either the state county level data could have been wrong or the government data could have been wrong. I looked at the trend over time. I looked at the changes. I looked at other sources. The government data was wrong. I can't remember what state it was. So the actual, it was reported by the Medicaid. I believe, I've been out of it so long, but the government agency that runs Medicaid, as at a national level. That data was, I was very sure, 95% sure, looking at all the evidence, that it was incorrect, and the county level data that the state sent me was right. So just no matter where your data comes from, unless you collect it yourself personally, assume it can be wrong. Whether it's the government that creates it, whether it's someone on your team, even if they're very good at their jobs and you think that they would never make a mistake, always assume that they might make a mistake. Because when you give results, it's, and I mean, it's a bad way to say it, but your butt is on the line. When you report results, if someone else made a mistake that contributed to the results that you have, then it's on you. It's not on them, because there's a lot of ways to find mistakes. And if you didn't find it, that's going to be your fault, not their fault. So always assume somebody is wrong until proven otherwise, is my suggestion to all of you. And if you don't follow that, you're going to learn the hard way. CMS, Center of Medicaid and Medicare Services. That's who, it was CMS data that was incorrect. So that was just a little foray to try to explain to you that data is not always right, no matter where it's coming from. Okay, so you'll remember from t-tests and of the other statistical models we went over, often there was an assumption that your data is normally distributed. So what I'm showing here, you can find a correlation without actually testing whether it is significant or not. Correlation gives you a lot of information, and sometimes you don't really need that significance testing. However, if you want a p-value, which in a lot of cases companies do want that p-value, there are two extra assumptions that are not included in just finding the correlation. So these are assumptions for significance testing of a correlation, but not the correlation coefficient. Okay, so in that case, your variables must be normally distributed, which if you have questions about that, you can go back into prior videos. The other thing that is really important, and we'll see this with linear modeling, it's very important there too. Your variables must demonstrate homoscedasticity, and that means that they have equal variances. You might be asking why I would use a term that is maybe confusing, and probably not the best term to say that they are equal variances. The reason I'm telling you this is because a lot of statisticians will refer it to as this name. So you need to know that homoscedasticity means that they have equal variances. If it's heteroscedasticity, that means that they have unequal variances. Over here we see homoscedasticity. So what that means is the, I guess, width, you could think of it as, of this distribution. So how far apart the top lines and the bottom lines, it's evenly dispersed over here as well as over here. Down here we're seeing the data at 80 to 100 is a lot more spread out than at 0 to 20. That's a problem when you look at significance testing of a correlation coefficient. So that's what I mean here. And I'm pretty sure my spelling was right in that case. So that is heteroscedasticity versus homoscedasticity. You need equal variances, which is homoscedasticity. Are there any questions about that? Okay. So sometimes in a lot of cases, assumptions or rules aren't important. I recommend paying attention to them because they really do actually make a difference. If you run a statistical test when you shouldn't be, you are going to have biased results, and they might not be just biased by a little, they're going to be biased a lot. So in a lot of cases, you're going to have to make a judgment call in these cases like this. Um, Something is never going to be perfectly like have equal variances. This is you're never going to see in real life. However, this is a pretty extreme case of heteroscedasticity. This is the case where you would want to draw the line and you would have to make a change to your model to account for it. In a lot of cases, they look at robust standard errors. So if you want to know more about that, it basically you have to meet a harder barrier or a harder cutoff to get statistical significance. In some cases, that can be used for significance testing in these cases, although it is not ideal. But when you see something like this, that really does mean that you should stop and think about running the test. It's not meaningless in these cases.